In this video, we want to talk about the distance problem. And so the idea here is we want to find the distance traveled by an object during a certain time period if the velocity of the object is known. Okay, so we know how fast the object is traveling. We want to figure out how far did it travel. And so this is kind of a reasonable thing, as you might know how fast a car is driving, and you might want to know how far did it actually go. Now, if velocity is constant, this is pretty easily found, because velocity is equal to the distance divided by the time. And so rearranging this, distance is equal to velocity times time. And so if the velocity is constant, we just take the velocity times how long it was traveling for, and we get the distance that it was traveling. Now, the issue is the velocity is not usually constant. And so because of that, we have to kind of improvise. And so what we're going to do is we're just going to kind of assume it's the same velocity for a set period of time, and then immediately shifts to the next velocity, kind of making it kind of jagged in how it accelerates, rather than smooth transitions. So let's look at an example to see what I mean by that. And so suppose the odometer on a car is broken, and we want to estimate the distance driven over a 30-second time interval. The speedometer is checked every 5 seconds to find the following. So we have the time, and we have what the velocity is at that time. And now, in reality, you'd probably measure things in miles per hour on the speedometer. We're not going to worry about changing units. We're just going to give it to you in feet per second. If you needed to change units, you can just use a simple change of units. So 1 mile per hour equals 5,280 feet per 3,600 seconds. And so you can just kind of shift things to make the units right. And so you want to shift things, if you already, so that the units of time are the same between the two. And I've already done that for us, just for simplicity's sake. And so at time 0, we're going 25 feet per second. At time 5, we're going 31. Time 10, we are going 35. Time 15 seconds, we're going 43. At 20 seconds, we're going 47. 25 seconds, we're going 45. And at 30 seconds, we're going 41. And again, we are in feet per second because I've already done the shift to make it in the right units. And so now, during the first 5 seconds, the velocity is not going to change much. So we can just kind of assume that the velocity is that fixed 25 feet per second over those 5 seconds. And if we make that assumption, then in the first 5 seconds, we would go 25 feet per second times the 5 seconds that we're traveling, and so we'd end up traveling 125 feet, just using that distance equals velocity times time. And similarly, for the second 5 seconds, so from 5 to 10 seconds, we can just assume we're going the 31 feet per second for that entire interval, and then we suddenly shift up in speed. And so for 5 seconds to 10 seconds, we're going to assume we are going 31 feet per second, so we have 31 times 5, which is 155 feet. And so we go about 155 feet in that second set of 10 seconds. Well, we can do this for all the other time intervals as well, and then just add them all up, because if we go 125 feet in the first 5 seconds, 155 feet in the next 5 seconds, and so on, you just add them all up, you're going to get the total distance that you traveled. And so we're going to have 25 times 5 plus 31 times 5 plus 35 times 5 plus 43 times 5 plus 47 times 5 plus 45 times 5. And we do end at the 45 times 5 because that goes from 25 seconds to 30 seconds, and so that's the ending period. We're ending at 30 seconds, and we've reached it after that point. And so if we add all of these up, so this is going from 0 to 5 seconds, this is 5 to 10 seconds, this is 10 to 15, this is 20 to 25, oh, this is 15 to 20. This is 20 to 25, and this is 25 to 30. And so if you add all of these up, we get 1,130 feet. Okay, and so we end up going 1,130 feet. But in reality, there was nothing special about assuming we were going the beginning velocity on each of these time intervals. We could have just as easily thought of going the end velocity. And so if we use the end velocity, we'd have 31 times 5 plus 35 times 5 plus 43 times 5 plus 47 times 5 plus 45 times 5 plus 41 times 5. And so again, we're just assuming that instead of going the 25 seconds for the first 5 seconds, we're actually going 31. We immediately jumped to the 31 and went that for the first 5 seconds. Immediately jumped to the 35, went for that for the next 5 seconds, and so on. So this is from 0 to 5. This is from 5 to 10. This is from 10 to 15. This is from 15 to 20. This is from 20 to 25. And this is from 25 to 30. If we add all those up, we get 2,110 feet. Now, because we don't make these jagged changes in speed, neither of these are going to be quite right, but they're close. Okay. And so now, one thing that you may notice is that this is very similar to what we were doing with the area problems from before. And in fact, it is almost the exact same thing we were doing before. Because if we were to draw the velocity function, and so if we draw our velocity function, what we see is that we have the following situation going on. And I'm not going to draw this perfectly. I'm just going to give a rough estimate of what's going on, kind of. But if we draw, if I can draw it accurately, if we draw our velocity curve, we see what we're doing is on the first one, we were taking left endpoints and just finding the areas of the rectangles. And so that's what we were doing the first time, and then on the second one we were taking the right endpoints. And so we're really just finding the area under a curve when we're doing these distances. Namely, we are finding the area under the velocity curve. And so it turns out that the distance traveled by an object is between, over a time interval, over the time interval t equals a to t equals b is equal to the area under the velocity curve from t equals a to t equals b. And so if we want to find the total distance traveled by an object, it's really the same as finding the area under the curve. And so in particular, we can write down a limit to do this. And so, just using what we talked about before, we're going to let the v of t, it's going to be the velocity function. And then delta t is going to be the change in time. What we have then is that the total distance is equal to the limit as n goes to infinity of the sum from I equals 1 to n of the velocity function at t sub I times delta t. Well, I'm just using t's instead of x's here. But this is just our area formula from before. And so we can figure out the total distance traveled by just splitting up into smaller and smaller time intervals, finding the velocity on those smaller and smaller time intervals, and then computing the limit of this sum. And so it's the same exact setup as what we had before with the area problem. And so we've seen now these two different situations that are seemingly unrelated that in fact are solved in the exact same way. And so in the next video, we're going to discuss this idea more in general of this idea of taking a limit of a sum like this to find areas under curves and distances.